Our last section here, we are covering this idea of uniform circular motion. This topic of circular motion will pop up again in Unit 5, and there's a whole unit, Chapter 9, with rotations. So a brief introduction here, and really why they put it in this section is because when you go around circles, you can see that the velocity from point 1 to point 3, or 3 to 5, or 5 to 7, all the velocities change, meaning that their direction is changing, or their speed could be changing. So you could be accelerating because of speed change or a direction change. Talk about things going in uniform circular motion. What we mean is that when you go around the bend, you're going at nice steady speed. And there's two terms you want to know when we're dealing with things going in circles. The first is time. The time to travel around a circle once is known as its time period. We measure those in seconds. Could be minutes or hours, but it's a unit of time. And the other thing we want to worry about is the distance traveled around a circle, which we call the circumference. So when we go around an entire circle, the circumference is the perimeter of the circle, which can be found by 2 pi r. So when things go around circles, they have what we call a centripetal acceleration, meaning that objects are accelerating towards the center of the circle. Centripetal, I remember as P pulling in towards the center of the circle. It's a center-seeking acceleration, and the centripetal acceleration equation is given there as v squared over r. If you want to go with units, we'll show you some unit analysis to show it's still meters per second squared. But in this case, if you change your speed or you decrease your radius, the centripetal acceleration of the object will increase. So that means if you go faster, like if you go twice as fast, the centripetal acceleration will be about 4 times greater. But if you cut the radius in half, that also doubles the centripetal acceleration. Play some ratios there and show you how that works. Where we get this idea of the formula for centripetal acceleration is from similar triangles, and so I'll do a proof of that to show you that your velocity at one point versus your velocity at a second point can give you a similar triangle to what we see with your position at point 1 and then your position at some point 2. Like a satellite moving around the Earth, objects want to leave the circle in straight tangent lines. Do not like to stay in circular motion. Think of it as your inertia. Your inertia says keep doing what you were last doing. So this satellite wants to keep moving forward. Its inertia says keep moving forward, but there's something that's going to cause it to accelerate in towards the center of the circle. Another thing you can deal with here is tangentially accelerating, meaning that you could go around the bend and start going around the bend at 40 miles an hour and end the curve at 70 miles an hour. So that means that you've increased your speed at the same time that you're changing your direction. So you have two accelerations happening, a centripetal acceleration inwards and a tangential acceleration tangent to the curve. And that's really just your change in velocity over time. So really your speed with respect to time. So in this example here we have an object that is moving around a circle. You can see the velocities at 4 different moments in time, and all the velocities are tangent to the circle. So they can be called tangential velocities or linear velocities because the object wants to go in a straight line away from the circle. If you wanted to calculate how fast this object's traveling, well, the distance you're traveling is, we said, the circumference, so 2 pi r. The time to go around once we call the time period, so that's just t. Distance over time here gives us our speed, and since we're going uniform speed, those arrows are all the same length. But what is different about those velocities at each point is their direction. Since they have different directions, your velocities change from going to the right, to heading down, to heading to the left, to heading up. And we showed before with motion diagrams that we could take a starting speed and an ending speed and find the difference in those velocities to solve for the acceleration. Vf minus VO puts us with a change in velocity up and to the left. That means as it goes around this portion of the curve, the object has an acceleration in towards the center of the circle. So that is a centripetal acceleration. However, the objects don't have to go the same velocity every single second as they go around a bend. You could be going faster or slower as you round this bend. So you do have that centripetal acceleration, but we could say that this final velocity is greater. So what that means is as you're centripetally accelerating around the circle, you're also linearly accelerating or tangentially accelerating along the curve as well. The centripetal acceleration is the inward one, and the tangential acceleration is the one that lines up with the circle. So that means that you could have two accelerations on your body as you round the bend. So the resultant of those two would give me the true, real acceleration. So if a problem says you're going around a bend, but you're also speeding up, you're getting two pieces of information. You get the centripetal acceleration, which comes from that v squared over r that we'll prove in a second here, and you get the tangential acceleration by good old-fashioned change in velocity over time. Once you have those two pieces, you have both legs of a right triangle there, since they are at right angles with each other, so you can use your Pythagorean theorem and trig to solve for the true acceleration of the object. If the object was slowing down, the tangential acceleration would be against the motion, and your real acceleration would be back. We need to prove how we get centripetal acceleration to be v squared over r. So the proof can be seen in this circle. You can see that there are two position vectors, your initial position vector and your final position vector, which really for this is the radius of the circle. And you can see the two velocities, your initial velocity and your final velocity as you go around that bend. The nice thing about the initial and final velocity is that they are the same magnitude, just like the position vectors are the same magnitude. If I would take position vector 1 and position vector 2, I could say that this line here in, let's say, green would be my change in r, my displacement. And as I did that displacement, I've also swept out an angle of theta. I could also look at my two velocities. I can say my final velocity minus my initial velocity gives me a change in velocity. And similarly, as I went through that displacement, I also changed my velocity by the same angle. So what we get here is this idea of similar triangles. And since the legs of the triangles are identical, this leg and this leg because of the same speed, and this leg and this leg because of the same distance from the center of the circle, we can write a ratio of these similar triangles. The ratio we could say would be the change in velocity divided by one of the velocities is equal to the change in position over one of the position vectors, because they're sweeping out the same angle in the same motion. So if I wanted to solve for my change in velocity, I can rearrange this and get a change in velocity to be change in r over r times v. But if I want to define this as acceleration, change in velocity must be divided by time, which means this whole thing over here must be divided by time. And what you can see with the highlights is a change in r with respect to time. Change in r with respect to time is velocity. So really, what you're going to be given here is acceleration is the velocity of an object multiplied by its velocity divided by its radius, or v squared over r. And again, centripetal acceleration must have units of meters per second squared because we know that is what acceleration is measured in. So if we look at this, velocity is meters per second, squaring that whole quantity, divided by radius, which would be meters. So when you square that, you've got to square both quantities inside. One of the meters is going to cancel out, and you're left with the same exact units. If we make up an example for something that is centripetally accelerating, you go around a bend with a velocity of 66 miles an hour, around 30 meters per second, and let's say that the radius of our bend is 15 meters. It's about 50-foot radius on our circle. When we do this and we put it into our centripetal acceleration equation, it's a very simple formula. You square the v and divide by r. So you do that, you end up with 60 meters per second squared. It has the same units as acceleration, but it's a little bit different in kind of its meaning. When we go around the bend, we say we go the same speed every single second, but there's an acceleration associated with this. What this is indicating is how quickly your direction changes as you round the bend. And that's a pretty high acceleration. If you remember Earth acceleration, our Earth can only accelerate things at around 10 meters per second squared, at best. Technically, the centripetal acceleration of the problem we just did is accelerating things at 6 Gs, which is 6 times what gravity can do. Just by things going in circles, we can get higher accelerations than what gravity can do. And if you were going around a bend at 6 Gs, you would definitely feel 6 times heavier than you normally do. One last thing we said, we could look at ratios for the centripetal acceleration equation and just understand what's going to happen to your centripetal acceleration by changing a few factors. What I mean by that is if we, say, double our velocity, put a 2 next to v, what I'm going to have to do is make sure that I square everything that's in the velocity. So what that gives me is a 4v squared divided by r. If on the right side of my equation I've got 4, that means on the left side I've also got to have 4, which means that if I double my speed, I now have quadrupled my centripetal acceleration. We can also play that ratio game by doubling the radius. So if you have a much bigger radius, what happens to the acceleration? Well, if I have 2 on the bottom, on the right side of my formula, that means I have to have a 2 on the bottom of the left side of my formula. When I double the radius, I actually half my centripetal acceleration. But of course, we could do multiple things at once. Let's say we triple the velocity, but cut the radius in half. We play the ratios for this. 3 squared is 9, and 1 divided by a half actually is multiplying by 2, and then you're left with your normal v squared over r. So really, if you triple your speed and cut the radius in half, you didn't just 9 times your acceleration, you actually 18 times your centripetal acceleration. Your centripetal acceleration increased by 18 just by going 3 times faster and cutting that radius down by 2.